this video, we continue to study metric space. So in the last video, I actually forgot to mention one definition about metric space. Yeah, we are talking about metric space, but I forgot to mention the definition about metric space. I only introduced the definition for metric, right? But metric space is actually quite easy to understand because if you're given a set, the set contains several elements, right? Some points or spaces, some points or some functions or sequences, and the metric or the distance function are some criteria for criteria to measure the distance between each two elements in that set. And if you are given a set and a distance function or a metric such that all the points in that set satisfy the three axioms, or the metric actually satisfies those three axioms, then the set and the metric together, these two are called a metric space. So it's like so typically it's what I was saying is that a set equipped with a metric is a metric space. Okay, so we actually can make this thing a bit more complicated because in the last video I only introduced the set is only given by like one set X, right? The space only given by one set X, but it actually can be a bit more complicated by taking one point which belongs to a product space. So now suppose we have already two metric space, which is X and Y, each equipped with a metric dx and dy. The way we define product space is simply taking one value from each set. So the point is now given by extracting x1 from x and y1 from y. And now we want to calculate the distance between such two points, x1, y1 and x2, y2. And we already know that x is a metric space and y is a metric space, right? So even if I don't give you the definition for the capital dp, d1 or d2 or d infinity, I think we can actually guess because x1 and x2 are from the same set, and the metric dx works for x1 and x2. So with dx you can actually calculate the distance between x1 and x2, right? And with dy you can calculate the distance between y1 and y2. And you cannot actually calculate x1 and y1 or x1 and y2. You cannot calculate the distance between these two, x1, y. You cannot actually calculate the distance between some points from x and some points from y, right? Because they are from different sets and they satisfy different metric. And it's like they are from different dimension. You cannot add them up. It's like someone's height and someone's weight. They are kind of like different, or from another perspective, you can imagine it as like they are perpendicular. So you cannot, if this one is 3, this one is 2, you cannot add them up, right? But if you have like this one is 2 and this one is 3, then you can add them up because they are in like the same direction, right? So what I want to say is that we have no idea about the relationship between x and y, the relationship between dx and dy. All we know is that x1 and x2 the distance between x1 and x2 satisfy dx, and y1 and y2 satisfy dy. So I think it's very reasonable to think about d1 to be dx x1 x2 plus dy y1 y2, right? And d2 is going to be taking the square root of dx x1 x2 squared plus dy y1 y2 squared, right? And similarly, if it is dp, then it's given by dp, sorry about that, it's given by dx p to p's power x1 x2 plus dy to p's power, and taking the power of 1 over p, right? And for d infinity, the distance is going to be maximum of dx x1 x2 dy x1 x2. So generally, if you're given a product matrix, you are actually required to calculate three distance. One distance is the distance between x1 and x2 with respect to dx metric, and the second one is the distance between y1 and y2 with respect to dy metric. And after that, you have to calculate for d, capital D, and for capital D with respect to the subscript p, right? So this is product matrix. And after introducing that, we are going to move forward to space of functions. Well, for space of functions, let's first think about space of points, which is what we introduced in the last video. And space of functions were given a continuous function. You can actually consider it to be a set of several continuous points, right? And for the discrete points, we use sum. Then for the continuous points, we somehow, I think a lot of you will come up with the integral sign, right? We are taking the integral. But the point is, we are taking the integral from which value to which value, and what is the integrand, right? So first of all, we have a small definition saying that, this symbol say from 0 to 1 is defined to be the collection of functions defined on 0 to 1 to infinity, to are real numbers, and all these functions are continuous. Okay, so the way we define dl1 fg, different functions f and g, is going to be taking the integral from 0 to 1 and taking the absolute value of the difference of f and g. So just imagine if you are given 2 points. Suppose for same x. So maybe fx x naught, fx naught here, gx naught here, and you want to calculate the difference between 2 points. You are taking simply the difference between these two values, right? And now we are kind of like we're not considering those discrete points, but the a continuous line or continuous curve. So we immediately think about taking the integral of it, right? Okay, so this is dl1, and dl2 is gonna be, I think you maybe already know, taking the integral from 0 to 1, the integral is gonna be fx minus gx, taking the absolute value of it, and square it, dx. And this is dl2. For dlp is the same. So it's like first taking the integral from 0 to 1, and the integrand is gonna be the absolute value of the difference to the power of p, and then taking the power of 1 over p. So this is gonna be dlp. And for dl infinity, well, the maximum would appear, right? So actually the dl infinity is gonna be maximum of, well, x is in 0 to 1. Maximum of the difference, maximum of the absolute value of the difference of x and g, f and g, sorry. So now this is dl infinity. And you can check that dl1, dl2, dlp, and dl infinity are all metrics on, so these are all metrics on say 0 to 1. Just remember, we are simply talking about continuous functions. So the set contains only continuous functions from 0 to 1, or as long as the function is continuous and 0 to 1, then we're done. See you in the next one.